chapter sent in by one of you from a 10th grade physics textbook.
You know, it's funny. We use electricity every single day, but rarely stop to think about what's actually happening behind the scenes.
It's like magic, but with, well, less glitter and more electrons. So this chapter, it starts off talking about electric currents and circuits, and it took me back to being a kid learning about those tiny particles zipping through wires.
It's amazing how something so small can have such a huge impact.
Right. And get this, the chapter mentions that just 1 coulomb of charge, you know how we measure electric charge. Well, it's made up of, get this, 6 quintillion electrons. That's a 6 with 18 zeros.
It's mind-boggling. We're talking about an unfathomable number of electrons moving around to power our world. It's really incredible when you think about it.
It is. And speaking of incredible, there's this interesting tidbit about how even though we know electricity is all about the flow of electrons, which have a negative charge, the conventional direction of the current, like what you see in diagrams and stuff, it's actually the opposite of how those electrons are flowing. It's like, did scientists just get it backward?
Well, sort of. You see, electricity was discovered way before scientists knew about electrons, and to be honest, they just guessed at the direction of the current flow.
A 50-50 chance, huh?
Exactly. And they happened to guess wrong. But imagine trying to change it now. It would be a monumental task, to say the least. So we stick with the conventional direction, even if it is a little counterintuitive.
It's like a little physics secret. So we've got all these electrons moving around, but what's actually making them flow in the first place? That's where electric potential comes in, right? Like, it's the driving force.
Precisely. Think of it like a ski slope. The steeper the slope, the faster the skier, right?
Because they have more potential energy at the top.
Exactly. Similarly, a greater electric potential difference between 2 points in a circuit, the bigger the push on those electrons, the greater the flow of charge, and the more current you get.
So it's all about that difference in potential, that push that gets those electrical charges moving. But for them to have somewhere to go, you need a circuit, right? A closed loop so they can keep on flowing.
Exactly. Like a racetrack for electrons. You break the track, and the race stops. Break a circuit, let's say, by hitting that light switch and that flow of electrons. Kaput. No more electrons moving, no more current. It's as simple and as complex as that.
It's like those electrons need a traffic system too, right?
Yeah.
And that brings us to something that always felt kind of mysterious. Resistance.
It's a bit like the unsung hero of the electrical world, isn't it? I mean, without resistance, those electrons would be on a one-way trip to chaos.
And it wouldn't be very useful, right? So how does the chapter explain resistance? Because honestly, I remember learning about Ohm's law in school, but it was always just, well, a formula to memorize.
Ohm's law is actually one of the most fundamental principles in electrical engineering. This isn't just some theoretical equation. This is the key to understanding how voltage, current, and resistance actually work together.
So it's like the instruction manual for making electricity do what we want it to do.
Precisely. We often use the water analogy to explain it, likening voltage to water pressure and current to the flow rate. But what's amazing is how Ohm's law allows us to calculate and predict how electricity will behave in different situations.
Like having a roadmap for the invisible, right? You can actually map out how the electricity is going to flow. And speaking of seeing the invisible, the chapter mentions an experiment where students get to test how different materials and wire sizes affect resistance. That's pretty cool getting hands-on with it.
Absolutely. Because it's one thing to read about resistance, but actually seeing how it changes with a thicker wire or a different type of material altogether, that's when it really clicks.
Totally. It reminds me of those science fair projects, building a basic circuit with a light bulb and then playing around with different variables to see how bright you can make it.
Exactly. It's about connecting the dots between theory and the real world.
And that brings us to a really important point. Resistance isn't the bad guy. In fact, we need it to design safe and effective electrical systems. It's all about finding the right balance.
Absolutely. It's a fundamental property of conductors that we have to work with, not against. And that's especially true when we start talking about arranging resistors in circuits, in series or parallel, because that's when things get really interesting.
It's like we're taking those basic building blocks and creating a whole electrical city. Instead of just one path, now those electrons have options, different routes they can take.
Like we're building a network of electrical freeways.
And just like with real highways, the way those paths are laid out, whether it's series or parallel, makes a big difference.
Absolutely. It's like comparing a country road to a bustling city center. They both get you from A to B, but the experience is totally different.
The chapter gave the example of old Christmas lights. When one bulb goes out, the whole string goes dark.
Series circuits. Each resistor connected one after another, so the current only has one path. If it breaks, game over for the entire circuit.
Single-lane road with a traffic jam, everything comes to a standstill. Thank goodness for parallel circuits then.
Right. It's like having multiple routes so that even if one is blocked, traffic can still flow on the others.
That's why our homes are wired that way. Can you imagine if your fridge went out every time you turned on a lamp?
Talk about inconvenient. Parallel circuits really changed the game, letting us power multiple things at once, no problem. Now that's something we really take for granted.
For sure. And speaking of things we take for granted, what about the heat electricity generates? I mean, ever touched a phone charger that's uncomfortably warm?
Happens all the time when current flows through a resistor, some of that energy becomes heat. It's just physics at play.
And sometimes we actually want that heat. Toasters, ovens, even those old school light bulbs, they all use it.
Precisely. We've literally designed appliances around this phenomenon to make our lives easier and more delicious, I might add.
Delicious is right. But the chapter also mentions that this heat can be a problem if it's not intentional.
Exactly. And that's where understanding Joule's law becomes crucial. It helps us predict how much heat will be generated and design electrical systems accordingly.
So Joule's law is like the heat safety guide for electrical engineers.
You could say that. It boils down to the fact that the amount of heat generated depends on the current, the resistance, and the time the current flows.
So a thicker wire, which means lower resistance, would generate less heat than a thinner one with the same current. That explains those chunky cables on some electronics.
Exactly. It's also why we have fuses in our homes. They're designed to melt and break the circuit if things get too hot, preventing damage or even fires.
Tiny little safety heroes. We've covered so much in this deep dive. It's incredible to think about those invisible electrons powering our entire world, flowing through circuits, encountering resistance, and making our modern lives possible.
It really makes you appreciate the brilliant minds who unraveled these mysteries. And who knows what the future holds? As we create even more advanced technology, who knows how else we'll be using electricity?
It's an exciting time to be plugged in. Thanks for joining us on this electrifying journey into the world of electricity. If you want to delve even deeper, check out the show notes for more. And until next time, stay curious.